So I have a skip list visualization pulled up on the left and a coin flip simulator pulled up on the right that will be used to determine the number of linked lists into which we insert a particular element. We first insert 20 with the predetermined coin flips 110 or heads, heads, tails. Next, we go ahead and insert 40. Before inserting 10, we will determine the number of linked lists that we've inserted into by flipping the coin. Our coin flip sequence is just a singular tail, so we'll only insert 10 into the bottommost linked list. Now, with any insertion, deletion, or search, we start a traversal to the left of the uppermost linked list in a node known as the sentinel. Next, the idea is to make comparisons restricted to the linked list layer that we're on until we move down to the next linked list. The next key in the first linked list is 20, which is greater than 10, so we know we must insert 10 between the current and next key, but we don't know the exact place to insert yet. So we move down to the next linked list to get a bit more precise. Now the next key in the second linked list is 20, which is greater than 10, so we move down again. The next time we try to move down, there isn't another linked list available, which signifies that we've reached our base linked list, and this contains all of the elements in the skip list, so we can just insert like we would in a regular linked list at this point. And we know that the target is less than the next element in the linked list, 20, because we tried to move down, but it's greater than the element we're at. So we insert 10 directly to the right. And we only need to insert onto the first linked list because we just flipped a tail and no heads. So now we're going to try to insert 20 again. But this time we're going to see that the algorithm determines that 20 is already an element in the skip list. And so it just won't insert it because otherwise it would be a duplicate in the list. Now, even though skip lists are technically allowed to contain duplicate elements, this visualizer doesn't allow for it, probably due to the fact that the visualization is focusing on demonstrating skip list efficiency, and containing duplicates would really only slow down the searching process, even though it would allow for a bit more flexibility in the data structure. So next we proceed to insert 5. Then we'll insert 80. Next, we'll delete the 20 that we added. Now we insert 100. So after inserting 100, we will reinsert 20 with just predetermined coin flips 1 and 0, which represents heads and tails. Now again, we start at the sentinel and make comparisons with the next key in the linked list. Now the next key to the right is actually positive infinity, and this positive infinity is just placed at the end of all of the linked lists and the skip lists, pretty much for comparison purposes. And as we can see, positive infinity is greater than 20, so we move down to the next linked list. And the next key in the second linked list is 40, which is greater than 20, so we move down again. And the next key in the bottommost linked list is 5, which is less than 20, so we move to the right. Now, we move to the right again at 10 because it is less than 20, and the next key is 40, which is greater than 20. So this time we move down, but there is no other linked list available to move down to, so we insert 20 directly to the right in the bottommost linked list. Now that we have determined the exact position where 20 goes in the skip list, it is easy to determine where to insert 20 in the higher level, less complete linked lists. So we need to insert 20 into the next higher linked list because we flipped one head before flipping tails. And to do this, we traverse backward in the list until we arrive at an element that is placed in more than just the bottommost linked list. So this allows us to move up to the next layer, and we know that 20 must be inserted in between this element and the next element to the right, just based on our previous comparisons. So we insert 20 directly above the other 20, and since our next coin flip after this heads was a tails, we are done with the insertion. So next we'll insert 30 using randomized coin flips again. So our next step, we will delete 5. First, of course, we have to search for 5 in the skip list in order to remove it. 30 is greater than 5, so we move down. And once again, 30 is greater than 5, so we move down again. And in an ideal world, we wouldn't have had to make this same comparison twice, but our skip list is not quite evenly distributed. So next we compare 5 to 20, and we find that 20 is greater. So we move down to the bottommost linked list. And the next key is equal to 5, so our algorithm moves to the right. And since 10 is greater than 5, we try to move down, but we can't, so the search is finished. And now we just have to check if the element we're at is equal to 5, and it is, so the algorithm removes it. We only have to remove it from the bottommost linked list because 5 is only present on this one layer. Now, this process actually took longer than if we had a singular linked list, just simply resulting from the fact that 5 happens to be at the very beginning of our list, and we didn't need to traverse all those layers. For our second to last step, we go back to insertion, and we insert 50. For our final operation, we're just going to perform a search for 80. In the top linked list, we find that 80 is, of course, greater than 30, so we move to the right. And here is where the efficiency of skip lists can really be seen. When we're searching for an element that's further down in the list, such as the 80 we're searching for now, it would be inefficient to compare it to every single element in the list before it, and that's what a simple, just regular linked list would do. Instead, hence the name of skip list rather, we get to skip the elements in the beginning and in this instance just go straight to 30. And once we compare 80 to 30, we never have to compare 80 to any of the elements that were less than 30 as we would have had to if we only had access to just the linked list at the bottom. None of our remaining steps, unfortunately, are more efficient than a linked list, but this just results from the fact that our particular linked list has, or particular skip list has a somewhat uneven distribution. But, the power of skip lists is still clear. Next, we can see that 80 is less than infinity, so we move down twice, and 80 is greater than 40 and greater than 50, so we move right twice, but it is less than 100, so now we can move down to the bottommost linked list. And the element to the right is indeed equal to 80, so we move to the right. And even though we have technically found 80 at this point, the algorithm still continues because it must be certain that we've reached the bottommost linked list. So it finds that 100 is to the right is greater than 80 and tries to move down, but it can't, which signifies that our search is done. To finish off, I'd like to further discuss the efficiency of skip lists. We know that the time it takes to search linked lists is linear related to the input size, but this is not the same for skip lists, as I'll explain. When we were searching our skip lists, the number of comparisons we had to make in each layer was not in any way related to the overall input size. In fact, the expected number of comparisons on a layer of any skip list is 2, and the number of layers is always expected to be less than the list size itself. Here, for example, we only have 4 layers but 7 total elements. This kind of relates to the fact of the coin flip procedure resulting in the expected number of elements on each layer to be 1/2 that of the previous layer, which means our expected number of layers is the log base 2 of the input size because of this whole halving procedure. And to get the total number of comparisons, we can simply multiply the number of comparisons per layer times the number of layers, meaning that the expected number of comparisons is just 2 times the log of the input size, and this logarithmic time growth of skip lists is certainly slower than the linear time growth of linked lists, which makes them more efficient at any decently large input size.